And so, hello everyone, and tonight we're going to look at the training of neural networks. Now, tonight's lecture will be sort of bitty. There's a lot of little different parts to it, and there's a lot of sections that I'm going to come to that I'm going to say to you, you really need to go and look into this a little bit more. I'm really only going to be giving you maybe a very brief overview of some of the parts. So, but we'll get going on it anyway. And the first thing that we need to discuss when it comes to the training of neural networks is to discuss about how you might do things to the data before you start in order to make things easier. Now, we've discussed this in many cases before to do with machine learning. And here we're looking at it with regard to deep neural networks. But in many cases, the sort of things are the same. We're talking about how we would treat what sort of treatment we would give the data before we might start. So particularly if you took things like images, what sort of things would you do to them? So previously we talked about the idea of feature scaling, and what I've done here is I've shown you an example where with just two features in this particular case, and what we're suggesting here is that your raw data might be something like this. So it's distributed in this way. Now remember that I've contrived this example. So and I'm going to show you more of this example later on. And while I've contrived them, this is nonetheless the sort of thing that you might see, except that we would be dealing with far more features than simply the numbers that we're dealing with here. So the idea is that if we want to do something like zero centering, what we would normally do is we would, along each feature, so from there to there, we would subtract the mean value. So the mean value along the X and the mean value along the Y here, we would subtract both those from the data. And that might give us the sort of thing that we have over here. You can still see it's distributed in that general direction there, but it's had the means subtracted from it in each case. Okay. What we might do then as well is we might want to scale it in some way, in some manner. Now, when we say scale it, we're talking about, changing it to some sort of standard deviation of, let's say, a standard deviation of 1. So that would be the case along each feature. So if we think about that being a feature there and that being a feature there, what that would mean is that we would more or less scale it along that axis and then scale it along this axis, and that's the sort of result that we might expect to see there. Now, with any of these things, you might think, well, surely this sort of thing is easier to separate or to classify than something like this, but in actual fact, this is generally easier to deal with, because what they'll then do is look at this as if it was zoomed in. So they'll look at it, but they now have to look at a much smaller window that they're going to have think about what they're going to classify, rather than having to worry about trying to classify things over here. So that's generally two of the things that you'll have done something quite similar in your own machine learning assignment that you did earlier in the year. Now, there are other things that you can do. One thing we didn't get a chance to go through in this semester is principal component analysis. And the idea there is to try and look at the data and see, are there any redundancies, and what are the general trends of the data? So I think you can all clearly see that there's kind of a principal axis that goes along there, and then maybe an orthogonal one, or at 90 degrees an axis that goes along here with regard to describing that data. So obviously we're only dealing with two-dimensional data here, and what PCA would then do is it would reorient the axes to line up with those principal components, so that we then see that it would be along this sort of axis there and then along that sort of axis there. And obviously this would be a smaller component than this one here. So if any of you have ever done anything to do with eigenvalues or eigenvectors or things like that in the past, or maybe a singular value decomp, that's great. Okay, so I'll kind of go back here a second. I think we were just talking about PCA here. So principal component analysis, the idea here, as I say, I didn't get a chance to go through this during the course, and I'd like to have had, but it's a linear technique, right? So basically all it's doing is it's just changing around the axes. It's not warping the space in any way, but it's changing around the axes so that it lines up with the principal directions that the data might lie in. So we can see here, for example, that it's found that it should have one axis there and maybe another axis here, and this axis is a good bit smaller than the other one. This is only two-dimensional data, so therefore we should only end up with two principal components to this. But you may find that when you do principal component analysis, particularly in a very high dimensional space, where you might have 20 or 30 dimensions or maybe even higher, that the data actually doesn't lie in certain parts of the space. You might find that some of your principal components are 0, in which case or some of your components are 0, some of your decomposition is 0, which basically means that you wouldn't have anything any data lying in that particular direction. And if we do that, what we can do is we can actually remove those as dimensions from the data, and it can be one way of reducing the dimensions in the data. It's a purely linear technique, and much of what neural networks do is to do a similar sort of thing, but in a non-linear way, where it might find that the data is lying in some lower dimensional space, but that lower dimensional space is not a linear space. So if you've ever done anything to do with like eigenvalue decomposition or something like that, you might find, that this one here, that would be your kind of largest eigenvector, and it would or to be, these two would be maybe eigenvectors, and you'd have your largest eigenvalue along that and a smaller eigenvalue along this. And if you find that some of those are 0, then what you can do is you can, as I say, you could remove them. Now the point here though is that if you put them along that axis and that axis like that, and you do the similar thing to what we did with the scaling here, well, you're now scaling with the data lined up with the axes, and what that will mean is that this from there to there gets changed into having a standard deviation of 1, and this from here to here gets changed into having a standard deviation of 1, and what you end up then is something that's much more circular. Now they refer to this as whitening, which is basically that the data tends to be all lying kind of within a circle or a hypersphere if it's in higher dimensions. Once again, there's no problem. This actually makes things easier rather than harder in terms of the data classifying things, because it really only has to look in a small area. And none of the data, it's when you move and you scale the data, you don't ever end up with a situation where some of the data ends up in a different ordering. Okay, that doesn't occur. So it still makes it actually easier to try and separate out the data, particularly if you're doing something like a classification task here. Okay, so those are some of the sort of pre-processing techniques that you might do on your data before you start. So if we talk something like pre-processing for convolutional neural networks, in practice for images, what we'd normally do is only the mean centering. Now there can be situations in which you could go beyond that, but generally just the mean centering will do the job, and that's what most of the systems that have won the ImageNet competition have done this sort of thing. So AlexNet just subtracted the total mean of all of the pixels in all of ImageNet, was effectively what they did. VGG subtracted the mean per channel. So in other words, they calculated a separate mean for red, a separate mean for green, and a separate mean for blue, and you can see those mean values there. And what they did was then, and those are you can actually use them yourself if you want. You can just subtract each of those. Whatever pre-processing you do for training, you must do at inference as well. So that's important, because when you then go to test an image, you need to make sure you've done the same sort of pre-processing. So in the assignment that I've given you there to do some transfer learning, you're going to be using a pre-trained VGG network, and therefore that has already learned the data, as making the assumption that this pre-processing has been done, which means that any new data that you're going to try and learn on, you're going to have to do the same sort of pre-processing to it. Now, one of the good things about Keras and TensorFlow is that they actually have libraries there that when you download the they have access to downloading the pre-trained networks for these, but they also have standard functions which will do the pre-processing for whatever that type of model was that you had. So if it's a well-known model, the chances are they have a function there for doing the same pre-processing, and you don't have to write your own. So don't be reinventing the wheel from that point of view, but you still have to do it. You still have to be aware that has to take place. So the next thing, as I said, we're going to be kind of jumping to lots of different sections here when we as we go through this lecture. So the next thing is, how do we initialize the weights in a network? Now, as I say, when you're doing your transfer learning, you really only have to initialize the weights of that final layer that you're going to replace. You don't need to, in fact, you don't want to initialize the other weights because you're going to use those pre-trained weights to be in the correct spot. But if you're working from scratch and you want a network to learn, what you're going to have to do is you're going to have to initialize the weights to something. And the first assumption people make, and a lot of machine learning techniques would have used the idea of just initialize all the weights to 0 and work from there. This sounds fine, it's zero centered, but the problem is not so much that all the weights are 0. That'll be dealt with by the fact that if it gives 0 as an output, then that's clearly going to be an incorrect output, and for each of the different weights, that's going to be incorrect by a certain amount in terms of the loss, and therefore you have you'll have a gradient there because it's still wrong. Even though it's 0, it's still wrong, and it's wrong by a certain amount, and therefore you will still have a local gradient. So that in itself is not really the problem. The problem is that they're all set to the same thing. Now, if all the weights are set to the same thing and you want each of your different convolutional filters to be looking for different things, I mean, it makes no sense to have 256 convolutional filters all looking for the same thing. You clearly want them all looking for different things in order to make best use of them. But if they're all set to the same value to start off with, then they'll all have the same gradient associated with them, and therefore they'll all get the exact same update, and what will happen is they will all learn exactly the same thing. So therefore it's not a good idea to have all the weights set to the exact same thing, 0 or otherwise. So don't set everything to the same value, or they will all do the same thing at an update step and then continue to do that. So what about the idea of using something like a 0 mean but from a small Gaussian? So the idea that in every direction you have, I'll maybe just draw this rather than just using that. You use a kind of a Gaussian. You've got a 0 mean here, and you say a small standard deviation, so small SD. Okay. What about that idea? So in deep networks, when you've got a small weights, what will happen is that if they're very, very small, you'll get smaller values out, and that's as you go through the deep network, and each one of them is small. What will happen is you get small multiplied by small multiplied by small multiplied by small, and that tends to accumulate so that, you know, numbers that are less than 1 tend to get smaller and smaller and smaller as they go. That's not such an issue, except for the fact that you get an awful lot of these kind of almost 0 activations. So this is different from 0 weights. The upstream gradient could be large to tell us that we have a big loss, but backprop multiplies that by the local gradient, and because the local activations are small, you're generally going to have a small local gradient in that case, or it can start to vanish. And it's because more or less that as you make the change, because the weights are small, you get a smaller value. So for some of our nonlinear activations, these small ranges are almost in the linear range as well. So if you take some of the things like if you take a sigmoid, which goes, well, I'll draw it a bit better than that. It kind of goes up and down like that. This section here in the middle, okay, that section there is quite linear, and so therefore if you only have a very small range over that, you're not getting much of a non-linearity in there in order to make the change. So ideally we don't want all of our weights being in these saturated levels, but we want, we do want things to be pushing towards those, so that you get the maximum out of your range, and you get the non-linearity to start doing something. So from that point of view, you want it to spread out pretty well over those, and therefore we'd like our values to be not too small, but also not too large, as we're going to see on the next slide. We want it to be kind of just in the middle. So for some of our nonlinear activations, these small ranges are almost in the linear range as well, and so this can lose us our nonlinear complexity, and it's difficult to learn our way out of it. Okay, so if we go for large, so we're saying, well, why small, why not large? Okay, so generally big weights are also trouble, right? So they push. what will happen is if you've got a big weight and then you multiply that by the activations coming from the previous layer, you get a big number, and that tends to push them into the activation section. So once again, just to draw some of the activation here, depending on which type of activation it is, you can end up with a lot that are in this saturated zone, simply because our weights are getting our weights are causing activations that are quite large. So they push a large proportion of the activations to saturation in the nonlinearity, and there's no gradient at the saturation itself. So ideally what we want is we want to be kind of in this zone here, really is where we want. We don't want the situation where things never saturate, or that we don't have some of them going into saturation. That can be a good thing. At the end of the day, you do want to be getting a bit on either end. You just don't want a situation where everything's in this linear range, or this kind of linear range here, or everything's pushed way out here and you only have a few activations in between. Second thing is, big weights can lead to big activations, which can lead to big updates, and the network can become unstable with this as well. So if you have big weights, you can make changes very quick, because if you have whatever size gradient multiplied by the size of the weight that's already there, because remember, you're always taking a proportion of that, you can end up very quickly getting out of control. So if any of you've ever done control systems, you'll probably be aware that when you set your poles and your poles in particular, that if they're bigger than a certain amount, that you can have a situation where it quickly gets out of control. So normally, if you're drawing those on something like a Laplace diagram, you draw them on the left side of the diagram. If you're familiar with those, in digital systems, you draw them inside the circle. If you're not familiar with them, don't worry about them. But there's a stability and an instability there, and the same sort of thing can happen here. And if you remember, regularization tries to keep the weights small in general. So it tries to keep the weights from getting out of control in a large sort of way. Okay. So is there a just perfect? Is there a way that we can get it just perfect? Because one of the problems is that if you set all your weights in exactly the same way, what can happen is, we'd like them to be in a fairly small range, but that fairly small range, then as it pushes up through the different layers, can have a different effect. So we really need to kind of think about how it affects per layer, and where exactly it's positioned. So there's an idea called Xavier Initialization, which is a paper written by this guy Xavier Glorot, and I think that's Joshua Bengio, but I'm trying to remember. I think there's two Benjios, because it could be the other Bengio. I think they're two brothers. So the basic idea here is that we should take into account the number of weights when deciding the range of the initialization values. So small number of weights at a layer requires a large initialization to fill out the space, and a large number of weights needs a small range of values for initialization. And the idea here that we're getting at is here that if you take a kind of a range in here in something, right, and we'd like to fill out the range from there to there. If we only have a small number, the chances of many of them getting out here into this extreme range and out here into this extreme range is less. Therefore, you might want to set that to a larger initialization so that you spread out on the space. Meanwhile, if you've got a lot of weights in that area, the chances are that if you take from a Gaussian, remember that your Gaussian looks something like this. So if you have relatively few, the chances are most of them will be in here. But if you have a good number, if you have a large number, you'll get a few out here at the extremes. So therefore, we tend to take into account how many weights we're dealing with before we when we want to determine what sort of initialization to do on it. Okay, so a small number of weights at a layer requires large initialization to fill out the space, and a large number of weights needs a small range of values for initialization. So at each layer, you divide the normal distribution by the square root of the fan-in when drawing samples to apply weight. So that idea of fan-in is probably something that many of you, if you've done electronic engineering, there's a lot of that idea with regard to the number of signals coming into a system and the number of signals going out, particularly in digital systems, and the load that will be on the system. So very similar here. If you've got a lot of weights coming into the system, coming into a particular layer, you take that into account. So you divide by that. So that the bigger that number, then the smaller your initialization can be. And if that's a small number, the bigger your initialization can be, as in the bigger the width of your initialization. So with each layer, divide the normal distribution by the square root of the fan in when drawing samples to apply weights. That's what Glorot found. There is a modification to this that was introduced by Keming He in that paper. I think that was the ResNet paper. There could have been another one, but certainly Keming He wrote the ResNet paper. I've it linked there, but I've forgotten which paper it was. The idea here was that they suggest that you do a further divide by 2 in terms of the fan in. So it's very similar to what Glorot is suggesting. It's just that a further division by 2. And this is if you're using the ReLU activation. Now the reason for that is that if you consider the ReLU activation here, what we have is a situation where we come along here and then we go up like that. Okay, that's the ReLU. And so where most of them which were zero centered would have something there and something there, the ReLU, everything in this region here is going to be removed by the ReLU, whereas everything here will be used. So really we're expecting maybe only half of them for something to actually happen. And therefore for that reason they're saying that what you should actually do is use twice the number in order to make sure that we have enough of them to go out throughout that space. That's the idea. Okay. Like with many of these things, once you can read the paper and so on and these things, but usually what happens is that you've got a library function there, you have a few different options of what to set as your initialization, and you can literally just fill those in as options. Okay, so we discussed the idea of pre-processing the data before input. Okay. And we said that each new layer creates a new representation of the data. So this idea that as you pass through the layers, you create a new representation and then another representation and then another representation. Now, if we pre-process the data before it comes in, so we're trying to say, well, if we take something like images, what we want to do is we want to do some sort of pre-processing to make it easier on the first layer. It might makes sense that after each layer, when we have a set of activations, that we might, it might be nice if we could have done some pre-processing on those, because they may not be ideally set up for the next layer. So this is kind of the idea of batch normalization. It's to try and in some way normalize the data as it goes into the next layer. So so what if you started with one of those intermediate representations? So let's imagine that you're 5 layers in and you have some intermediate representation. Let's imagine that that was your actual starting data. Well, if that was your starting data, what you'd be likely to do is do some pre-processing on it. So what we're saying is there a way that you could kind of do that pre-processing as you go before it goes into the next layer in order to make it easier for each one in order to make its changes. Remember that this doesn't really change around where the parts are at this stage. We just want to condense it into a region that makes it nice to deal with. So to some extent, this is the idea of batch normalization. You rescale the activations to be best set up for the next layer. So the question then is, what is the best range for each layer? Okay, so how do you decide that? Because the thing is, it's fine to say on your first layer that you're going to zero center it, and you can also decide that you're going to do some sort of scaling on it if you want. That's fine. But does that make sense for each of the subsequent layers? That may not be the case. It mightn't be obvious because you don't know what features it's going to create and you don't know how it's treating those features. So remember that we're having trouble enough understanding these learned representations. So to make an assumption about those learned representations that it might like to be, I'm just checking that I'm still going there. It might like to be within a certain range. That may not be a valid assumption. Okay, but if we had some way for it to try and figure out what was best for it, that would be the ideal. So why not learn to have the best normalization? And that's what the idea of batch normalization is. So there are some issues here. Firstly, with ImageNet, we knew the mean and the standard deviation of the whole set. Okay, but training during training, we only train on a batch at a time before doing an update. So this is the idea, and I'll come back to this again. I think I've mentioned it a number of times that when we're training these large networks, let's say we have 10 million images that we're going training on for the sake of argument. We clearly don't put 10 million images through the network, calculate the loss for all those 10 million images, and then do an update. Okay. Instead, what we do is we take a batch of those images, put them through, get the loss, make an update. Now that changes the entire network, and that changes the entire network based on a small subset of our data, a very small subset. It's only a batch, and because it then moves the entire network to some position, we then go again and again. So therefore, the network is constantly changing what might suit it at any given time, and therefore it's a bit of a difficulty for us. We can't possibly know ahead of time what would be the ideal place to move these to. So we're going to have to learn these as we go. So we can't say we know the mean and standard deviation for the activations for the whole data set at any given time. That's going to change as the network trains. The whole network undergoes a lot of change over the course of an epoch. Just to remind you that word epoch stands for a it stands for one run through the entire data set, and we would normally do many epochs before we would finish training. So instead we use the batch statistics as a proxy for the whole data set statistics. So remember that the data set and the statistics of it are trying to give us, we're trying to learn a model from that would then suit any data that comes from that distribution. But remember that the training only gives us an estimate of what the entire set of images, the entire set of images that could possibly be created. It only gives us, it only has a subset of that which is covered by the training images. If we look at a batch, then we've got a much smaller set of statistics trying to cover that entire range. So, but what we do is we use the statistics off the batch to try and give us a sense of the overall statistics of the system, and from there try and make sense of where our activations are going, and then try and decide, well, where do we want to move our activations to in order to make them best set up for the next layer. And as I say, that will change over time. So what we do for each batch is calculate a per channel mean and standard deviation. By per channel, RG and B would be 3 channels, but if you go into the next layer of a network, you might have 256 filters, and therefore that would be 256 channels. So I use the word channel or filter or feature. Each of those I use as a kind of they're just other names for each other. So so you basically calculate it along each feature. Then we mean subtract, and we divide by the standard deviation to give the activations for a batch a mean of 0 and a standard deviation of 1. So you're familiar with that idea, that in other words, that if you have some data here, and it's let's say it's at a mean of 5 and a standard deviation of 3. To get this to be a mean of 0, we would first subtract 5, so we would say minus 5 from every value in it, and that would move it down in this direction so that it's now centered on 0. And what we would then do is divide every value by the standard deviation, and that would give me a standard deviation of 1. And it basically would drag in each of these. It would drag it into that. Now, if it was a standard deviation that was less than 1, and we divided by that standard deviation, it would then expand it out to be 1. So the idea is then that because it's centered on 0, we can then do that multiply, but you have to do that in the right order. So the first thing that happens with batch normalization is it takes the mean and standard deviation for each channel. It subtracts the mean from each channel to 0, center it, and then it divides by the standard deviation of each channel to make sure that all the data is now at a mean of 0 and a standard deviation of 1. I've drawn this as a Gaussian. There's no reason to assume that the data would actually be a Gaussian. Okay, so we're using the parameters as if it was a Gaussian, but there's no reason to assume that it would be that. But nonetheless, it will have an effect of kind of condensing it into that sort of range. So even if it was something a little bit more uniform, like this, well, that's fine. It would still compress it more into a range or drag it out into a range. So it basically means that the next layer can kind of concentrate on a particular area of the data that it's going to spend its time and not be worried about searching all over the space for the data. So that's the first thing. It zeroes it and then expands it out to that. But of course, with time, we might find that any of the given layers might not want it to be zero-centered and at that deviation. They might expect it to be somewhere off to the side. It's some other mean, and it could be different means depending on the different features. And they might also expect that it might be wider or narrower. So what we really want to do is we really want to learn where it should be. So remember, we calculate the mean and the standard deviation based on that particular batch that's going through. That's why it's called batch normalization. But we also overall, over time and over each batch, we learn where we then should move all those activations so that they then move into the right place to make it easier. So this is the formula here. We calculate our this is a standard way we would do. We add up all the values in each channel, and we divide by the number of them that there are, the number of samples. Then what we do is we use that and subtract it from each value, and then get the square of that, and once again divide by m. That's probably you may remember a -1 there on that. It would probably be the better way to get to get an unbiased estimate of that. But they may not do that in this case. They may be happy enough with a slightly biased estimate of the variance. What they then do is once they've calculated that, they subtract the mean in each case. So they subtract the mean there, and then they divide by the standard deviation. This is the square root of the variance, so that the variance is the standard deviation squared. So that will just work itself out. So that's the variance there. If we get the square root of it, that's the standard deviation. That's what we divide by. There's normally a tiny little number added there, and that's just in case the standard deviation turns out to be 0. Because if it turns out to be 0, you're going to have a divide by 0 and you're going to run into problems. So for that reason, they normally add in a tiny little value there just for numerical stability. Now at this point, what they do is they learn two parameters, which we'll call gamma and beta. And basically what they'll do is, once they've ended up with this value with a standard deviation of 1, so there with a standard deviation of 1, what they do is they then multiply by whatever standard deviation they require. So if they've found, during training, if it's found that what works out very well is a particular standard deviation, let's say a standard deviation 2, they'll multiply all the values by 2, and that'll widen it out again. And if they find that it should be on a mean of -3, well, then they'll shift it all down there by adding or subtracting some learned mean value as they go. So you can see what they do. They basically get the data, they shift it to be zero-centered, then they compress it or expand it so that it's got a standard deviation of 1. That's now you've got, with 0 is the identity for addition and subtraction, and 1 is the identity for multiplication. So this now means that once they're in that position, they can then move to anywhere else. So they can learn anywhere else to move if they want, or they can decide we're not going to move at all if that's what suits. So if it suits the next layer to have zero-centered and a standard deviation of 1, they can leave it there. Or they could just completely undo the original thing. So if they started with a mean of 5 and they moved it to 0, and they started with a standard deviation of 2 and moved to a standard deviation of 1, and it turned out that actually what was really good was what they had originally, well, then they can just learn that. They can just learn to undo it. Okay, and that's indeed what they'll do, what it'll do if it finds that that's the best thing to do. So what we've done is, as I say at this point, is we've done our mean subtraction and compressed it or expanded it to a standard deviation of 1. And at this point, what we do is we learn the best standard deviation to multiply the activations by. And that's in general so far. Remember that that's going to change, that can drift over time as each batch goes through. So as it sees a new batch of data, but also as the network learns what it wants. Okay, so the network is learning all the time from the information that it's getting and based on the loss that's there. And then we learn the best mean to add to this as well. So you got to do that in the reverse order. You start by subtracting the mean and then divide by the standard deviation. You then multiply by whatever new standard deviation you want and then add whatever mean you want. So you have to do it in the opposite order. So the learn parameters are for transforming it from a position of zero mean and unit standard deviation to something that's more desirable as it learns it. Normally, the batch norm layer is placed between the convolutional or fully connected layer, linear activations, and the that should be the non-linear activation. I should have wrote in there, so non-linear activation. So what they're saying is after the linear layer and before the non-linear activation, such as the ReLU or the sigmoid, they would normally put the batch normalization there. The thought is that it will learn how best to use that activation. So, for example, if it was finding that it was that from the previous layer we were saturating too much in going through the activation, we might find that it's better to push it into the better region or expand out into that region. There is another school of thought that says it should go after the nonlinear activation, so that it's in the correct position for going into the next layer, which is of course what we have in terms of our pre-processing. In truth, batch norm will normally help speed up training whichever place you put it, and while its effects may be different in different locations, the system will simply learn quicker with it. Okay, now the jury is still out as to whether it's better in the long run to do this, or whether the network might have learned something else if we didn't do it. And sometimes you'll find people will leave it out of certain layers because it maybe causes instability, and there are other effects from it as well. So it's not absolutely it's not a panacea for these things, but it certainly has seemed to stood the test of time and worked very well. One of the great things about it, well, vital things about it, we should say, is the batch normalization is differentiable. In other words, you can differentiate it. There is a derivative of batch normalization. That's important because you're going to put it in the middle of a network and you need to be able to calculate your gradients going back through it. So this is important as we need to be able to back propagate through anything we put in the neural network. So batch normalization would have to be differentiable for that reason. In fact, it allows for better gradient flow and really helps with the vanishing gradient problem. If you consider that idea where your gradients are very, very small, and that then multiplies by the local gradient, and therefore the upstream gradient becomes very small. In this particular case, it can have the effect on the gradients that it spreads them out again, and therefore it really had a very good effect in terms of solving the vanishing gradient problem. It also affects your hyperparameter choice. For example, and there are lots of hyperparameters. Where to include batch normalization, for example, is even a hyperparameter. But things like your learning rate and all that sort of thing, higher learning rates are possible with batch normalization because of the fact that it makes things easier on you. Initialization is not as important when batch normalization is used. If the network learns that batch normalization is not a good idea, it can kind of learn to undo itself, and that's what I was explaining there. It can kind of decide that it's going to undo whatever it did in the first place. That's not entirely true because of the fact that it calculates the mean and standard deviation of the current batch of statistics, whereas what it learns to undo is learned over the long term. So that those two are not exactly interchangeable, but they're not far off it either, because you tend to find that the batch is quite representative usually of the entire statistics. In most cases, we will have a representative batch, and in these cases it can learn beta and gamma that are simply the reverse of the scaling done at each batch. Batch norm is also considered to have a regularizing effect. So it's quite the same as regularization. And that regularizing effect means that it tends to generalize a little bit better. And the reason for this is that rather than rather than it getting to see individual samples which it can overfit to, instead it's getting some statistics that are related to the entire batch. And therefore, because it's related to the entire batch, you have this situation where your network is then concerned with generalizing to the entire set of statistics. So it's considered to have a regularizing effect. Now, the important thing here about this is that because it has a regularizing effect, if you've included regularization elsewhere within your network, for the purpose of regularization, you may need to tune that down a bit. So that lambda value that you normally use for deciding how much regularization you're going to have, you may need to tune that back a bit to use a little bit less regularization, because of the fact that batch norm is now also having a regularizing effect. So that can be a little bit of a problem. So batch norm can to some extent cause a little bit of underfitting, simply because what a lot of people do is they add a lot of regularization, and there are other forms that we're going to show you in a minute, and people throw all of these things at the network without realizing that they all have an effect maybe on the regularization, and you're kind of you maybe need to tone some of it back because of the fact that you're using these techniques for other reasons. So what happens then at inference? Because at inference you might be only putting a single image through. You're probably not putting a full batch through. So what do you do in that case? So what happens at inference time is that we usually use some empirical mean and standard deviation that we've learned from the training as a fixed value, so that you at each layer you subtract that and then divide by that, and then you still use the learned beta and gamma to move you to the next spot as well. So that's generally what happens at inference time. Okay. Now, so what I've done here is I've just I'm re-showing this example to show you the sort of thing that might happen at batch normalization. I've deliberately gone a little bit extreme with this example in order to just show you the as I say, this is kind of contrived, but just to show you how what batch norm might want to do. So previously we saw how we would zero the mean, and we would also scale it. Now what happens is, when we get a batch, you can see that this batch might be quite representative of that. In other words, that it's fairly well distributed across that full range. We're not seeing as much down here, but we're not too bad. I mean, this only goes as far as there, so you can see there that we're fairly well covering that range. On the other hand, this would be a non-representative batch, where it's all up in this kind of region here, so it's not representing the overall data. However, because the calculations are done on the individual batch, if we took this representative batch and we gave it a zero mean, so we zero centered it, and we scaled it so that the representation is only over maybe a standard deviation of 1, this is where we're going to end up. Now if we take this one here, this is what's going to happen in that case. And actually there's not a whole lot of difference between this one and this one, and that's simply because we've done our calculations based on the batch rather than on using the entire set, which we don't have access to. The second thing then is that we then learn, and you can see the gamma value that we would learn in each case. So we've learned a gamma value here of about minus 10 on that feature and plus 10 on this feature as regards to where we've shifted it to. And then I can't remember what standard deviation I've learned. So Vin is asking why we've lost some data in the second feature. So are you referring to this diagram here? Is that the one you're referring to, Vin, just so that we can be clear? The top one, this one here? Yes, okay. So I don't think we have lost anything in either of the features. Remember, the feature goes across that way and up that way. So we haven't actually, so if we take any of these, it still has information in both of them. So I'm not sure what maybe you're wondering why we've got fewer dots. Is that what you're wondering? Yeah, so we've fewer dots because if you imagine that this is my entire 10 million images, I can't put all 10 million of my images through the network before I do an update. It just wouldn't be feasible. So instead I take only a batch of those, and that's what this represents. So we only take a few of them, and it's meant to represent, they're meant to be representative of the full range. Okay, so as I say, with each of these, whether it's a proper representative batch, which it will be in most cases, or whether it's not very representative, in both those cases, when you do your mean and standard deviation of these, when you do the statistics of the individual batch, you'll move them along each feature, and they'll be more or less put here. What we then do is we learn, and what I'm assuming is that for some reason we've learned that a gamma value along this feature should be plus 10 and a gamma value along this feature should be minus 10. I can't remember what I set as my standard deviation as regards to expanding it, but you can see that they've both been more or less moved to roughly the same sort of range, if that suits. Now, as I say, this is a rather extreme example. What's far more likely to occur is that you actually don't learn to expand this too far in terms of your gamma and your beta value. It's much more likely that somewhere in this sort of range. But you can see a situation where it might find that it wants to put in some little amount, particularly with something like a ReLU, you know, where you're going along something like that on one of the ranges. Now I'd have to draw that. It'd be like this on this feature here. You might find that you might want to be more in this range because you're going to zero a lot of these, or it might find that actually there's a good reason that we don't want to activate for some of the things that we're finding, so we might want to move it the other way. In any case, it's not up to us to necessarily decide what we want. There's no point having one of these networks and then deciding what it's going to learn for us. The whole idea is that it shifts it into the rough range for us. Okay. So that's the idea of batch normalization. There are some other types. There's layer normalization, which we mentioned with the AlexNet, and it's basically the idea that what we do is, rather than us doing it across each feature and for that set of batches, we do it in some way across all the different activations within a layer. Okay, so it's just another way that we might do this. There's instance normalization. Sometimes it doesn't. It's not useful to do it across an entire batch. So it might, and I've used examples like this before. There's a particular thing, generative adversarial network called the Wasserstein-GAN, which requires, as part of its network, that we do it on an individual image at a time rather than over an entire batch. So we might just do it across the activations of a particular image. There's another thing then called spectral normalization. This goes back to the idea that I mentioned to you earlier of the principal component analysis and all those. When you do a singular value decomposition, these ideas, spectral, you'll probably come across this term before if any of you did discrete Fourier transforms and things like that, where you think of spectral in terms of frequency, but in actual fact, that idea of frequency is just one example of a spectral technique. And this is generally where we do something like a decomposition on our matrix, and we look at the individual singular values or eigenvalues if it's a square matrix, and it's basically looking at the different orthogonal components within it. So it's a little bit complex. But the idea here is that what we would want is that we would want none of those none of those singular values to be larger than 1. And so what we can do is scale those back to be smaller than 1. Normally you could just divide effectively by the largest singular value, and that will make all your singular values smaller than 1. Now, going back to our control system example that I mentioned earlier, you can have a situation where the poles in your system are, if they're too large, you can have this situation where the thing can get out of control very quick. So if you do this sort of normalization on your weights, what it can have the effect is that your network can't suddenly explode or get out of control, and that's kind of the idea of spectral normalization. Now, I should say, I'm not going to ask you about any of these in an exam because I really haven't given you enough detail to really understand them. The only reason I've mentioned them on this slide in this way is to just make you aware that they exist and that they might be something that you might have to look at some point in the future. I haven't given you a detailed enough explanation, and you can imagine that if I've only given you a sentence of one or two of them, I haven't really given you an accurate one either. So don't necessarily go with too much of what I said there. Just all I'm really giving you is the basic flavour of the idea behind them. Otherwise, I'd have gone into a lot more detail. So I said we'd be jumping around quite a bit. The next thing I want to talk about is regularization, and we've mentioned this quite a bit before as well. This is the idea where when you're training, you want to make sure that your network is not learning something that is overfit to the data. So adding terms to the loss function, such as a weight penalty, is the most common form of regularization. At least it's the most common form of regularization that is quite easy to control, but it's by no means the only way of doing it. So we looked at this the last day, where you can add a regularization term at the end here, which is basically you penalize it if the weights start to get very large. Okay, now you can kind of think about this a little bit like that. You don't want any of your weights to become, some of your weights could suddenly become very large, and if you set a squared penalty on this, it means that any individual weight that gets large, it's the square of that you get penalized for. So it likes to keep all of the weights fairly small, and this also has the effect of spreading things out a little bit more across all the weights rather than it being one individual weight. Almost all of these techniques, and we're going to see another one called Dropout in a while, they're based on the idea that it is far better to spread your learning as much across your network as you can, rather than relying on maybe a few filters that might do a really good job. You can think of this in terms of something like a sports analogy, where let's say if it was something like Formula One. I don't know whether any of you watch Formula One at the moment, but certain cars are very good in terms of their straight line speed, so their engine may be very good, and other ones are better in the corners. And you'll find that it's the car that is best across all of these that will generally do the best. In terms of football or something like that, you can imagine where if you've a team of 11 players and they're all pretty good, versus a team that has one star player who might be able to score the great goal, but if they're knocked out of the game in any sort of way, or if they're neutralized by people constantly marking them, then that team doesn't do as well. And we've seen this over the years. I think Germany do particularly well in World Cups, where they have they have a really good overall team, and then you have individual very good players like Ronaldo and Messi and people like that, who generally play on a team where the rest of the players might not be as good as them, and it's very difficult for those to do well. So it's very similar to that idea, where we don't want individual filters that are doing all the work for us. We want to try and learn it so that we spread it out across all the filters, and that if we knocked out any of these individual filters, that we would still do a pretty good job of learning it. And to some extent, this is the idea of the ensembles, that in other words, that whichever team you picked would do a better job, or would do a good job. But the idea is that we're better as a crowd or as a group rather than as an individual. So we've come across this idea in a few places. It's the idea of the wisdom of the crowd. I said to you before that this idea that if you ask anybody how many pennies are in a jar, or the weight of an animal or something like that, you see these at a lot of fairs. That what'll happen is that individually we might make a good guess at what that might be, but that as a group, if we were to take the average of all of those answers, we'd probably be very close to the right answer. So the idea here is that we could train multiple models. The stochasticity, in other words, the randomness will give us different optimized result in each case. So because we train multiple models, obviously, we don't want to end up with the exact same model trained each time. But because of the batch, because of the fact we're putting batches through in a random order, the chances are we'll get a slightly different model on each occasion. When we use some average or voting system between the different models at inference time, you might have 6 or 7 of these models. They'll all give slightly different answers, but we'll take a vote of them. And in general, this will lead to approximately about a 2% performance increase at test time. Say approximately because it obviously depends on how close we're getting up in the high values as to whether we get a 2% or maybe something smaller. But in general, it can give you that little extra edge that if you were trying to win a competition or otherwise, you might make a difference. Okay. So the idea then of dropout is a little bit like that idea said. If you were training something like a football team, you might drop some of your players in each individual, for each different match or each different training match, so that each player gets to learn to be as good as they can or gets an opportunity, but also that each of the different ones get to learn to play with each other. So very much similar with a neural network. The idea of dropout is that what it does is it tries to perform an ensemble within the network. So basically what it does is, as training is going, it randomly drops different filters. And you could drop as many as 50%. So you could decide you're going to have a dropout of 50% where you're going to only use randomly 50% of the filters as your training. And what it's got to do is it's got to still figure out how to get the right answer, even though it's only got 50% of the filters to work with. So therefore, the network must learn not to become too reliant on a few filters, but should be able to make the prediction based on whichever percentage of its filters that happens to be activated at the time. Now at inference time, we don't give ourselves that same handicap. We're allowed to use all of the filters at inference time, and that's a little bit like using the ensemble of systems at that time. So you have to reduce the overall value of the activations by the dropout used. So this is one of the things when you come to doing your inference, because of the fact that at training time you only have 50% of the activations, and then at test time you have all of the activations, the addition of all of them together lead to a bigger number. So what you've got to do is you've actually got to divide by half or multiply by 0.5 so that you lower the level of the activations overall. So it's like that fan in again, you've now got twice as many. Now normally what happens is we always want to optimize so that inference is very quick. So sometimes what they will do is they will they'll divide the activations at training time by half, or multiply them by, sorry, I think that what they'll do is they'll multiply them by 2 so that afterwards the opposite thing happens. And the idea there is that you do all of it during training, and then when it happens during activation, you don't multiply by anything, and therefore you end up with the same value. Note that also that Dropout itself has been patented by Google, because they were involved, and the people that now work for them were the people that wrote the paper. It's a little unclear why Google and other companies do this. Are they doing it because they plan to enforce the patent at some point, or are they doing it simply to protect from somebody else patenting it? Are they doing it just so that they build up a lot of patents? And what can happen is that a lot of these big companies, they hold a lot of patents so that it's kind of a mutually assured destruction, as they used to have with the nuclear powers, that if Google have a certain number of patents that Facebook or Twitter need to use, and Twitter have a load of patents, and Facebook have a load of patents, and whoever else might have a load of patents, then what happens is that each of them kind of ignore the other one using their patents, as long as they don't enforce the patents that each other company is using. So I think that's maybe the reason, but it's also obviously slightly concerning from that point of view that that what might seem like obvious ways to train these networks, they're all obvious after they've been shown, of course. That if somebody owns the patent for that, what then happens? And you'd be surprised that a lot of the other things that we take for granted with regard to these are all patented. So this is the idea of Dropout. You can see our standard neural network here, and what will happen is that Dropout will randomly decide not to use some of these and hope to still get the same level of activation at the end, or to still get the correct answer at the end. And then at test time, we use all of the weights together. So now I've mentioned gradient descent, and we've described that algorithm and how it works. And we've mentioned stochastic gradient descent, but just want to obviously formally do it here. So stochastic gradient descent, stochastic obviously refers to random or probabilistic systems. So gradient descent is an algorithm we've explained previously, but a variant is used for training most CNNs, is called stochastic gradient descent. Gradient descent would require us to take into account every sample in the training set to calculate the single loss and then do an update. Now the problem with that is that it doesn't make sense for us to send all of the samples through before doing an update, because we would be here forever. And the chances are that a batch of those is representative of the entire data set. Okay, it won't be perfectly representative, and depending on randomly what's in that batch and the order that they come in and so on, because obviously you've trained your network pretty well before you've seen some of your samples. So what we'll find is that will be somewhat edgy. So rather than seeing a kind of a slow, a descent down the gradient like this, what we're far more likely to see is something that kind of jumps as it goes down the descent. But we should see that in general the trend is down in this sort of direction. Okay, but we will see a lot of jumpiness in our thing, so it will go up and down from time to time, and that's because the next set might cause a bigger loss than the previous set, and so on. So gradient descent, or sorry, if we do an update after each randomly chosen sample, so let's say for example we did an update after every sample, so every individual image that's put through, then the order of the samples will have a large effect on the loss, because obviously the first sample that it sees, it's going to have a certain loss associated with it. It's going to try and minimize that loss, so that it's trying to minimize that individual image, and the next image mightn't have the same sort of loss at all. So therefore the network is automatically going to go in the direction of the first few images that it saw. So if we shuffle the samples differently, we'll have a very different outcome. So it'll have a considerable variance. For this reason, this is called stochastic gradient descent. Now, what we actually do is we do it in terms of a batch. So full data set versus single image update are the two extremes. Instead, we'll usually use a random batch of images to represent the full data set and then do an update. However, the order of the batches and the random nature of the samples chosen mean that the loss can have a considerable variance and is dependent on when in training that batch is chosen. So for this reason, we refer to gradient descent in this manner as mini batch stochastic gradient descent. Okay, so it means that we're using a small batch of them. Strictly speaking, batch gradient descent is when we update after all the samples are passed through. So unfortunately, that word batch is also used to refer to the entire set, which we normally refer to as an epoch, but it does actually, when we talk about batch gradient descent, we mean the entire set. So that's when we do an update after all the samples are passed through. Stochastic gradient descent means updating after each individual sample, and mini batch gradient descent, which we normally call mini batch stochastic gradient descent, this means updating after a small representative batch. So it's a bit confusing, the names, and in truth, when we refer to stochastic gradient descent, we regularly are referring to this catch-all term that generally means the both stochastic gradient descent and mini batch stochastic gradient descent. Okay, so in general, when you hear the term stochastic gradient descent, we're referring to the mini batch version of it, but in actual fact, the original terms came from very specific versions of these. Okay, so it's unfortunate, but most people, when they refer to stochastic gradient descent, they're referring to the mini batch version. Okay, now, there are a load of optimization techniques which I'm not going to go through, but there's a very good paper there by Sebastian Rudder, who is, I presume he was either a student or a postgrad at the time in NUIG, so that's the National University of Ireland in Galway. So our neighbours just about 90 miles south of us here. And there's another nice article there, 10 gradient descent optimization algorithms, a cheat sheet by Rami Karim. So there's a lot of different versions to this. Stochastic gradient descent in its basic form was found to have some problems whereby it was very influenced by if we had something like a valley that was occurring, whereby it was very steep on one feature and not so steep on another feature. And of course, if you've got millions of these features, you've got a problem. So what they had is this idea of momentum, which is, if we're going traversing down a valley, what can happen here is that you start going like that across it. But if you add a momentum term a little bit like a heavy ball, you can see how it would start to go and then would start to go down that sort of direction there. And then there were all sorts of different versions like Nesterov momentum, which kind of looked ahead to the different feature. And then some of these other mechanisms here, which took into account a little bit more the idea of saying, well, not every weight should have the same level of change associated with it because it's going in different directions and so on. I'm not going to say anything more about that because I'll say something inaccurate to do with one of the specific ones. But just to be aware that this one, Adam, tends to be the most popular at the moment because it just tends to work very, very well. So you can kind of keep that in mind. But that's a constantly changing field. One of the other things that people might do when training is that they might decide that they haven't got enough data and that they'd like to have more, but they don't have any more labeled data. So what they do is they augment the data, the labeled data that they have. So they use the same label, but what they do is they modify the data samples that they have in some way to create extra ones. They don't just create copies of them. That wouldn't be particularly useful. So if you'd like more data but don't have enough, you can consider data augmentation. This is where you make multiple copies of the labeled training data and make modifications to it. If after the modification it would still be obvious to a human viewer, so in other words, if you have a picture of a dog and you modify it in some way and it's still obvious to a human that it's a dog, then it should still be obvious to the a trained network, and therefore it works as an augmentation. If on the other hand you made some modification that was obvious to a human but wasn't obvious to the model, then clearly the model hasn't generalized well enough. So some of the examples of things that you can do are things like you could do random crops. So if you have an image like this and you decide to do different random crops of that image, so maybe one there and another one there and another one there and so on, these different random crops, as long as they still hold the data. Obviously you have a bit of a problem if you've got something like a cat in here in that image and it appears in the overall image but it doesn't appear in some of these other crops. That can be a problem, but generally speaking the crops that you're doing mightn't be as extreme as what I'm doing here. They might only drop a few pixels off each end. That also means that whatever it is that's in it will move to some extent within the image. The other things you might do is you might scale the image in some way so that now whatever's in your image could be bigger or smaller, and can your network deal with that? You might do rotations on the data, so can it still recognize it if the thing has been rotated in some way? A human certainly could. Humans can certainly see, can figure out what's in an image if you do a random crop, but also if you scale it and if you rotate it or if you translate it, move it around the image in some way. If you add noise to it, so just some sort of noise to the pixel data, normally a human can still figure it out. You can mirror it, so a mirror of a dog or a cat will still, a human will still recognize it as that. Just be wary if it's got something that's got text in it, or if it's something that doesn't make sense when it's mirrored, that can be a problem. So do be careful about what sort of data you do that to. You can also do lots of lens and perspective distortions and things like that. Stuff we'll be learning a little bit more about in multiple view geometry, and those of you that had me last year will remember some of those sort of distortions there. So you can do lens distortions and things like that to your data as well. Maybe change it to a more of a fisheye look or something like that. Can it, when it undergoes that distortion, human can still probably figure out what's in it. Can your network do it? So those are the sort of augmentations you can do, and you can create quite a lot of extra data from doing that. Once again, I mentioned to you that I've given you an assignment to do, and one of the things that you really need to do for that is to set up a data generator in Keras. Again, I think you can do those generators that you can augment the data so it can create different augmentations of it. You don't need to do that for the assignment that you're doing, or well, you may not do. You can decide if you want to do it or not. But generally speaking, there are systems for putting in those minor augmentations rather than you having to create all that data yourself. Some other tips and tricks. These are general things that I've kind of picked up from lots of different places, and you'll find an awful lot of places on the web where people will give you some tips and tricks. Most of them are the same in the different places that you go, but you might see a few different ideas in different places. And generally speaking, what happens with these ideas of tips and tricks and heuristics is that they work very well for certain models. On certain data sets, but that doesn't necessarily mean that they're universally a good idea. So don't get too wedded to these tips and tricks if they're not working for the particular example that you're going for. So one example is that use Adam first of all as your optimization technique rather than the more kind of vanilla standard stochastic gradient descent. And the settings for these are that there's a beta 1 and a beta 2 of 0.9 and 0.99. Now these are related to and you can use it with a learning rate of about 0.01 to 0.0001, so around about that sort of thing there. So beta 1 and beta 2, I'm not really going to go into detail on them, but they're related to how much momentum you're including. So therefore the 0.9 might suggest that you're going to take values from the last kind of nine iterations of your technique of your optimization algorithm, and that you're going to place most of the value on the current one and a little bit less on the previous ones going back the way. And the beta 2 is really just related to the second moment of that. I won't go into any more detail because otherwise I'll have to go way down that path. The other thing you can do is maybe when you're starting off your network, just to make sure it's working correctly, you can do a quick inference test. So if you start with a network that's just been randomly initialized and you put an image or something like that through it, you should find that it should give you a random answer. And what that basically means is that, let's say if you have 5 classes, it should give approximately 0.2 on each of those classes. It shouldn't be very heavily towards one and not to the others or anything like that before it started training. You can then do a little bit of training with your current learning rate, and you can check, is the training loss going down steadily? Now I'll draw you a graph on the I think it's the next slide. No, 2 slides away. I'll draw you a graph of how you might know if your learning rate is too high or too low or whatever. But you really want to see that the training loss is steadily going down for you, or otherwise you maybe need to relook at your learning rate. Check that your network has enough capacity. So in other words, is your network big enough to solve the problem that you're trying to get it to solve? And you can do this by deliberately getting it to overfit. So let's say, for example, you've got 1 million images in a training set. Well, you can take a very small, maybe 500 images or 1,000 images or something like that, and pass them through your network training just on those images. That means that your network is going to regularly see the same images, and it should be able to pretty much learn those images off so that it always recognizes something about those images. If it can't do that overfitting, it suggests that you maybe don't have enough capacity in your network. Okay, now it could also be something else, but that's one possibility. Now, once you've done that and you know your network is big enough, you need to go back to scratch and start again. You don't use those weights. That's just to kind of figure out before you get going too much. You might think that this takes up quite a bit of time, but actually, if you're learning on a very small set of images, then it can go through epoch after epoch very, very quickly. Now, you should obviously, if you've included some regularization, you need to turn off the regularization by setting your lambda value to 0 before you try to overfit, because otherwise you might find that it's not able to overfit to the data, but that's because you've set regularization to some level and the regularization is doing its job. Now obviously when you go to do your main training, you want to switch that regularization back on again. So if you can't get the loss very, very low or 0, then you likely need to rethink your architecture, or you've made some other mistake. So in other words, it should at least give you pause for thought. But remember, it could be something like your loss function or that is going in the wrong direction. Many solutions change the learning rate to a lower value when we reach convergence. So I think I've drawn you this before, but this idea here that you've got your training error here on that axis there, and what's happening is you're going down here and you start to converge to some value here. Okay, so after a while of that really not going down from there, what you can do is you can set your learning rate to a lower value, and what you'll generally find is that it'll do some similar thing again and then converge, and you can set it again and it'll do some similar thing and converge again. There's diminishing returns to this, and indeed you can go too far in trying to get this, in that what can happen is that really what you're doing is you're setting it so low that it's managing to overfit to the data again. So you don't want to push too far with this, but you can do this after a while, and if you see this sort of convergence happening, you can set your training rate lower. Now this if you're using the Atom optimizer, this generally isn't necessary, because Atom changes its learning rate depend on what the individual weights are and so on, and the gradients. So therefore, if it's not seeing a change in the gradients, it starts to do this in some manner anyway. Okay, so generally speaking, adding will mean that you generally don't have to do this. So all the time what they're trying to do is find algorithms and architectures that are somewhat robust to whatever or at least to a fairly large range of hyperparameters, so therefore that you're not so, it's, you know, that your job is not trying to find the perfect hyperparameter for whatever you're doing. And Adam is one of those ones that lets you away with quite a range of learning rates, and that you don't have to change it as we go. I did mention here that some suggest starting with a really low learning rate, maybe for an epoch or so, and the idea is that it tends to find the perfect way to go before you then start moving to a slightly larger learning rate, which you can then reduce with time. But so the beginning one of having a very small learning rate at the beginning is just maybe to set it off in the right direction. As I say, that's the intuition, but I haven't really seen a lot of theory behind it. It may exist. I may just not have read the particular piece of literature on it. But that's the kind of idea. As I say, I haven't seen much theory on it. So how do we know if we've set our learning rate too high or too low or just right or whatever? What are the indications? So generally speaking, you want to, when you're training, set it up so that you're not just looking at the training values coming out as numbers. You'd ideally like to see a graph of it over time so that you can get an idea of what's going on. Now, generally speaking, a good learning rate is going to do something along the lines of this. It's going to go down fairly rapidly. Now, as I say, what you're really going to see is something that's jumping up and down like this with stochastic gradient descent. But I'm going to draw the general trend here. And what you can actually do is you can decide to say, well, I'm going to do a smoothed version of my learning rate. So I'm going to take an average of the last 50 or 100 training iterations, so that you get a much more smooth version of what's actually going on, rather than get confused by seeing values going all over the place. So we expect it to go down fairly rapidly and then start to level out, and you get diminishing returns as you go on here, but it'll start to kind of converge. And as I say, at some point then you can decide, well, let's converge, I'll go down to something else. But that's generally what you want to see it to do. So this is your training error here. And this is your iterations. Iterations of your algorithm, so it could be batches, or it could be you could do this in depending on what range you are. You could be just looking at epochs here if you're going through a lot of it. Okay, so that's looking pretty good there at that, right? Now let's see something that wouldn't be working so well. Let's say you set it to it goes down pretty quick here, or maybe too quick, and then all of a sudden seems to kind of level out here like this. Okay, not going any further. This would generally suggest that it's a bit high. Okay, because you can see there it's gone down very, very quickly here because it was high, but then all of a sudden it hit this kind of thing where it couldn't get into smaller kind of crevices in the learning landscape, and therefore it kind of gets stuck and it can't go much more. So basically your problem is here that what you're finding is that it just can't get down to a low training error, and therefore it's not particularly accurate. It's kind of stunting its growth at some point. Now you can have worse than that. If it's very, very high, what you might find is that it goes down at first, but then all of a sudden starts to balloon up and do something like that. So this is too high. And we explained this before, this idea that if you're in some sort of a lost surface, and none of them are ever as nice as a lost surface as this, but what can happen is that you make too large of a movement in each direction, and you end up and you start moving and jumping back out of the thing. In other words, your loss gets higher rather than lower. So so that can happen if it's too high. If we're too low, well, what we tend to see is that it goes down all right, but it just tends to go down at a very, very, very sluggish rate. And, you know, well, I'm even maybe going a bit extreme. It might, or going a bit too easy on it. You might find that it's very much going in this sort of direction here. So, for example, you know, you might think, well, let's say, for example, that you set your learning rate for the sake of argument, to one of these values back here. Let's say it was 0.001. So 0.001. And you might say, well, let's just be on the safe side and say that I'm going to go for 0.0001. Okay? And you might think, well, this is on the safe side. Now, the problem with this thinking is that this is going to take 10 times as long. So if it was going to take you 10 days to train your network with this learning rate here, this one is now, so if that was going to take 10 days, this is going to take 100 days. Okay, and that's just not to be sniffed at all. Okay, so trying to find out at first, you know, what is a reasonably good learning rate before you get going. It's worth spending a day or two on that if this is going to take several days. And you know, many of the VGG and Inception, a lot of those when they were originally trained, they would have taken a few weeks to train on a number of GPUs. So this is not insignificant, and it's important to get that idea into your head that it's not a good idea to just get this wrong by a factor of 10 and think that that makes no difference, that it'll eventually get there anyway. Yes, it might, but it could be 10 times as long, and that can be a real problem. Okay, so that's sorry, I didn't write this one. This idea here, this is if it's too low. Now that might eventually, you know, it'll eventually get past the high one, because it will get there. It's just it could be a long way out here before it ever gets to it. Okay, so that's the idea though. So we leave it there for tonight, guys. Obviously the usual set of acknowledgements. I think I had this one in from a previous one because I didn't actually use them tonight, but all the other ones, I'm very grateful to them for their for the use of their material. Okay, so we'll leave it there, guys, and I'll chat to you next week. We'll have our last lecture next week.